But it is extremely important in these compound semiconductors. The charge collection is far from 100% complete. And you can see that here by using the depth information. What's illustrated are separate pulse height spectra looking down from the top, where if you look at one of these, this is the full energy peak. And if we blew up the scale, you can see a Compton continuum here and a backscatter peak here. And you notice that as you look at different depths into the material, the position of this full energy peak moves. It is not in the same position. And that simply tells you that electron trapping is going on. When the event occurs far from the collecting anode over here somewhere, you get a smaller average pulse than when the event occurred here nearer the anode, and so there's a shorter drift distance. Well, if you did nothing about this, this is now an imperfection in the detector that will spread out the full energy peak, and it will destroy the energy resolution. Well, there's obviously now a way to fix this electronically, because now you have separately the pulse height spectra at each different depth. This is stable behavior. It does not change dramatically over long periods of time. So it can be calibrated. So as an initial calibration can tell you how much of the signal is missing because of the charge trap, and that can be added back in electronically to compensate for the trapping. So it's a way of making what would ordinarily be a rather poor energy resolution into one that's much finer and much better. And I'll show some examples of those spectra in just a minute. This is just illustrating again the ability to separately measure both the position and the energy deposited in 3 dimensions. Now, gamma rays coming in to any gamma ray detector tend not to be absorbed in one place only, but rather they tend first to be Compton scattered, perhaps Compton scattered again at some other location, and then finally photoabsorbed at perhaps a 3rd or 4th position. So looking at gamma ray interactions almost always, except for very low energies, means that there are multiple points of interaction in the device. So you need, in order to do spectroscopy, to add together all the energy that's been deposited at each one of these separate locations. Well, in a standard germanium detector or sodium iodide detector, that's done automatically because simply the charges add up because there's a single output node, or the light adds up in the scintillator. Even though it may be made up of 2 or 3 individual light flashes, they add together to give the output signal. Well, here you're getting separate output signals for each one of the interactions, so they need to be recombined electronically. Here's the result, and first of all, this is not for multiple scatters. This is the small percentage of cases in which the gamma ray came in and interacted only once and was photoabsorbed. That might be 10 or 15% of the cases at CCM energy. And I don't know if any of you have, sorry about that again, I don't know if any of you have worked with CZT, but if you go out and buy the best CZT detector you can today, it will be what's known as a coplanar grid. We want to get into that later, we can, but I'm going to not get into the details. You can buy detectors of a few cubic centimeters with perhaps 2 to 3% energy resolution. And that's better, clearly, than most scintillators, but now with these new materials coming on the scene, it's less attractive because the scintillators are getting down to almost that same level. So in order to make progress with semiconductor detectors, one has to do better than the currently available coplanar grid configuration. Well, this configuration with separated pixels, I believe, has that strong potential. And here you see what the spectrum looks like if you only select those events which occur under 1 pixel. And you notice, in this case, a 0.7% energy resolution. And in fact, later results after this plot was made with some other ASIC refinements have gotten this down to just over 0.5%. I think that's extremely good for a room temperature semiconductor. And these are substantial volume. I don't see it on here. Several cubic centimeters is a typical size. Well, those are single pixel events. Eventually, you need to deal with the fact that most gamma rays interact many times. And here is the added spectrum from all events, whether they interact 1, 2, 3, or more times, and added together now. Unfortunately, in those cases, the electronic noise is now adding from each one of the separate interactions. So the energy resolution isn't quite as good anymore. It's deteriorated in this case now to 0.96%. Well, the object is going to be to get that lower and lower because it still is dominated by the noise level in the ASIC. And since these are very early ASIC designs, there is every reason to believe that clever designers who know much more than I do about how to design low noise circuits can bring that figure down to a much lower figure. And in that case, perhaps get down to something like 0.5% energy resolution. Germanium at cesium energy would have something like about a 0.2% energy resolution. So you'd still be about a factor 2 or more away from germanium, but this is room temperature and not cool. So it would have some strong attraction for portable instruments, for example, areas where the liquid nitrogen is a real hindrance. You can also look at some nice radiation physics. These are separate spectra sorted out by how many pixels fired. So you see single pixels at the top, and increasingly multiple events as you go down to each of the lower plots. And the point is that for single interactions, you get a lot of continuum because most of those are Compton scatters. Whereas when you get into the high order number of interactions, many more of those events end up in peaks because they are fully absorbed after previous scatterings going on in the detector. So you learn some kind of interesting tutorial information as well about the radiation interactions. You can also do particle tracking. This is an example of a muon passing through the detector with a couple square centimeter area. A few muons per minute pass down from the cosmic rays. And here's one of them caught as a track where you see its complete transit from one surface of the detector to the opposite surface. All right, moving on to other materials. Mercuric iodide is another tempting material. It's wide bandgap, and it can be grown in substantial size crystals. And again, Dr. Yamada has been one of those who have looked very closely at this material. It currently is not available as a commercial device, other than in very thin layers of 1 to 2 to 3 millimeters. Now, those can be useful for low energy applications, but not for general gamma ray spectroscopy. The hope is to make thick mercuric iodide, and this is, as you see, 15 millimeters. And remember now, this is mercuric iodide with an extremely high Z value for the mercury. So 15 millimeters is equivalent to perhaps 30 or 40 millimeters of germanium because of the much higher Z value. And In this case, a spectrum from a